Now we're going to go to a single node multi-core job. So this is often an OpenMP job. Gaussian is a common program that uses it. It's very popular among computational chemists. And there are programs that use threads. So here we see that in this example, for a 4-core OpenMP job to run, it needs a whole node. It has to wait until the whole node is available. So if you've seen earlier, an MPI job could start much earlier because it didn't have to wait until everything was available. It could start on day 1. While this OpenMP job has to wait until day 2 on the same cluster, because it has to wait until there is a whole node available for it to run. So these are basically single node multi-core jobs. All the threads must run on a single node. Now, all these threads share a single memory address space, or they can share one. For OpenMP, we could easily compile serial and parallel executables from the same code. And then OpenMP is the easiest methods of parallel programming, and it can be done incrementally. So you could parallelize part of your code while leaving the rest serial. So it's easier to do. But once again, it's not as flexible as MPI when you need to run your job. So how do you ask for an OpenMP job submission in Slurm? Well, you do it with a sbatch minus CPUs per task equals X. Now, the communication between parts of this job is done via memory in OpenMP.
Yeah, so Neil's running a workshop in the background. Won't talk to him. You'll hear him.
Yeah. So one could ask for a program to run a number of threads via environment variable. So you can export OMP num threads equals 8. But usually it's set to the number of requested cores. So you would do like an export ONP num threads equals, and then the environment variable Slurm CPUs per task. This will set your program to run the correct number of cores on the node.
But as I raise this and bring this up,
so some tips for running OpenMP jobs. Check the state of the cluster to see if your job will run quickly. If you have a number of OpenMP-style jobs, you should consider running longer jobs using less CPUs per job instead. It is faster and more efficient to schedule single or smaller processor jobs. And this advice may not apply when you need other resources, such as large amounts of RAM per job. Are there any questions? Okay. So we could look at hybrid jobs. So a hybrid job, basically, you can ask for 2 nodes with 2 processors per node. So here's an example. It's somewhere in between the MPI and the OpenMP. Oftentimes, it's both MPI and OpenMP, actually. So it's possible to combine OpenMP and MPI for running on clusters of SMP machines. You need more memory or other resources than is available per core. And there's advanced systems of running parallel jobs that could utilize the resources more efficiently. So communication between cores is faster than communication between distant nodes. And some of these systems include the Chapel language, as well as the partition global address space languages, PGAS, such as Unified Parallel C or Core Fortran. So some of these, there's training materials in WestGrid. I believe there was a Chapel course. If you're interested in using advanced parallel programming. So for the Slurm script commands, you could ask for n tasks equals x. So this requests x tasks. Once again, CPUs per tasks by default is 1. So this is how you would do your MPI jobs. If you ask for nodes, you ask that a minimum of X nodes be allocated to this job. You could ask for a node range. You have both a minimum and a maximum number of nodes. You can ask for CPUs per tasks. That request that a minimum number of CPUs are allocated per tasks for each task in this job. And you can have tasks per nodes, which minimum number of tasks be allocated per node. So all these you could use to have different types of requests. So if we ask for n task equals 1, that's usually a 0 job, because CPUs per task is 1 by default. If we ask for CPUs per task equals x, well, that's usually an OpenMP style. It requests x CPUs in one task on one node. If we ask for n tasks equals x, tasks per node equals x, it requests x CPUs and tasks on a node. If we do n tasks equals x, nodes equals 1, request x CPUs and tasks on one node. You could ask for that, yeah. I think I copied this slide twice. Okay, so we could look through the scheduling worksheet again. So here we have problem 7 through 16. But unlike so I would definitely recommend that you do these yourself. But I am going to go through these quite quickly right now with you because we have a time issue. So if we have to, so let's go and start. Let's submit. Question number 7 asks us to submit a 0 job that has a maximum hold time of 2 minutes, sleeps 30 seconds, is named my array job, and has 12 tasks. By the way, is there anybody that has any questions? Please speak up or ask it in the group chat. So here we ask for 1 task on one node, and task equals 1, nodes equals 1. For 2 minutes, we give it the correct name. We also set up a ask for an array, 1 to 12. We can submit this. Oh, right. Just like yesterday, we should probably add in the fact that we're running inside a reservation. So we could use those reserved nodes. And we could see that we have actually multiple pieces of this job starting. And we probably also want to run scontrol show job and the job ID. And we can see our scontrol actually has many array IDs. So we see many parts of it. And we can see that some of it are already completed. And we see that it's all done. What else we see is that we have a whole bunch of outputs. We have errors, and so as we see here, we have a dot. We have the Slurm Q7, the job ID, but we also have the array ID. So the -1 is the array ID. So you would have 1, 2, and so on. You would really like to do this if you're doing a parameter sweep or something like that, and you have an identical job with a whole bunch of different variables that you may want to input, for instance. So this is really great for organizing these things. I just erased most of those outputs, so we don't have quite as much messing stuff up. Okay, let's try job 2. Basically, we want to do the same thing, but we want to run at most two jobs at once. So how do we do that? Basically the same thing as before, but we have a %2 at the end of that. So it's array minus minus array 1 to 12 %2. And just like in the other one, we probably should now you should follow along. So you could be running these yourself while we're looking at this. Not only that, after this presentation is over, you'll have the opportunity still with that workshop reservation to do this yourself, or just even run the provided answers already. So we could see here that of this new job, my array job 2, we only have 2 running. Yes, my array 2 is still running. The first array job, the one we originally scheduled that wasn't inside the reservation, is also running as well. We can also run scontrol to show us information about the job. You can see that there's 2 running. Some are completed already. So, as we showed in that diagram, certain jobs can start, they could complete. This is just like having a whole bunch of 0 jobs, except it's a way of organizing this. It's also faster for the scheduler to do this, and it's fairly simple to do. So question 9, it asks us to submit a job. It has a new name. It's my array job 3. it asks for 4 tasks with indexes of 1, 2, 7, and minus 13. Oh. So other than putting in the reservation and my accounting group, you could put numbers in here, 1, 2, 7, and 13. I believe if you put a minus 13, it's going to fail. In this, you can't have negative numbers as array indexes. If you do put 13, though, it will work. Also, you may notice here in this example, we have a Slurm job name, Slurm job ID, and task ID. So in this example, we're going to write out the task ID. We can see these tasks starting. There's 4 of them right now. As control show job also, you can see you see all 4. And here you see the actual output. So you do see the array ID of being 1, 2, 7, and 13, and 11 for the same job. So the 13th one, it is my array job 3, the one we just started, part 9. Its job ID is 2,118,635, which is what it was. Its array ID is 13. So that's the output that was done by that part of the array. And this one was run on node 308. If you run it yourself, you may end up running on a different node. We have a number of nodes reserved. That's why 308 keeps coming up. Okay. So now we're going to run, for question 10, we're going to run job array with 2 tasks. One has an array ID of 1. The other one has task ID of 4. We're going to ask for 1 core per tasks. We're going to have a maximum wall time of 2 minutes. We want to get emailed. We want to call my array var job. And we'd like to echo out some information. Okay. Once again, we need to put in our reservation. We're calling it my array var job. We have array indexes 1 and 4. here we automatically print out the environment variables that were set by the scheduler. So Slurm job name, Slurm job ID, host name, the list of this job runs on the list of nodes, and it will list out their names. We'll list the number of nodes. Oh, there's a question. Yeah. So the question is, so you submit up multiple jobs with the array option. How do you indicate what to do with the job? And yes, that is correct. Markan said the correct thing. So basically, the same script gets executed multiple times, just with a different array task ID. And you could actually write your own script in such a way that you can use this. And I think that's question 11. So we started running. It's going to take us a few seconds to see what's going on. So writing a script to make use of an array job, you have to understand a little bit about Unix scripting to do so. It's not very difficult, but you have to understand how to write Unix scripts. We can see that these are running. Once again, S-control gives you a lot of information about your running job. The scheduler sometimes times out. Sometimes it takes a few seconds for it to respond, or it doesn't respond because it's taking too long. So there we see the jobs have run. Where am I output? Oh, there they are. So as we saw, inside the job we had just printed out all these environment variables. So let's give us a list of node names where each process of this job runs. So it ran on Cedar 308. The number of nodes that this job runs on is 1. The number of tasks inside this array task is 1. The number of tasks inside this array tasks per node is 1. And this task ID is 1. And then we've printed out all the Slurm environment variables. So we can see here that there's Slurm array tasks, but that shouldn't be confused with end tasks, which is another type of tasks that Slurm has confusingly named as task. And the same thing is true of here. Also, what you should notice is that the actual job name is different for each task. Just job ID is different for each array task. So in here, this array task is number 4. This array task ID is 4. It also run on Cedar node 308. Any questions? Okay. So now we're going to go into a fun example. So this requires you to understand scripting, but this is how you actually use these job arrays. So we're going to want to create a 0 job array that reads from a single file and runs a job for each line of the input. It's going to be named my input array job. It's going to have 4 tasks with 1 processor each. It should email you when you complete. And the file that is used is called input array. Now we're just going to have each job in the array double the first number and add the second one. And we'll run to see the output. And before we do that, let's clean up, because there's a lot of outputs. So we have an input array, just 4 lines of with column of number, 2 columns of numbers. So here is an example of how you would, say, do a parameter sweep. You can have a few different inputs, and you can, based upon these inputs, run a different, say, Monte Carlo simulation and write a different output. This is how you would use a job array with a single job array with getting multiple options in and running them. So once again, I'll have to edit it to add my workshop name and for it to email me properly. So how do we do it? We set up this job array of 4 tasks, 1 to 4. We have an output file, and we have a %a here, which is the array ID automatically in the output file. We'll name this job my input array job. Now here's a little bit of Unix shell scriptiness. Basically, we read the line, and we, based upon our array task ID, we get that line. So a job with a task ID of 1 will get the first line. A job array of task ID 2 will get the second line, and so on. And then we take that line and cut it apart, get the first field and the second field. And then we could use this. It's a math. So we use a command line calculator and just multiply the first line twice, first variable twice, and then add the second variable. So this is how you would, use a job array. Is there a question? And here we have our outputs. So we got that line. Its array ID was 1, so it's the first line. And the first line of input was the number 1, space, and number 11. And then, we did some math on it. So you can see that's correct. That was the first one. In our second example, we grabbed the second line. Fourth example is the fourth line. So this is a typical way of running it. It's also possible that we would have wrote it all to one file, but it all depends on how you want to run this. This is a simple example of using an array job. And the nice thing about this is that, unlike all the other ones, the outputs, well, they are all with an array ID, easy to organize. Is there any question? So let's go on to an example of an MPI job. We're going to submit a job called startmpi.sh. So this one is there with all the answers as well. But this is the basis of this question. And we're going to see what's happening. Clean first. So once again, we need to edit this. Put in the fact that we want to run inside the workshop, reservation, and my appropriate email address. So in this case, it's going to run an actual job. This is an example which actually runs a job called MPI sample, which is actually right here. So as you can see, there it is. So in this example, we're going through this question as if we're running some MPI job. We didn't program it. We don't know what's going on. Yeah, did I put that in? Oh, yes. I need to run start. Now, this job is going to run for a while. Now we could go through and edit the start.mpi.shell and change the number of tasks. Basically, that was this right here, to 4. Now, this MPI job, as I said earlier, it automatically goes in. And it starts the correct number of So this MPI job is looking for the scheduler environment variables, and if you set them properly, it will use the number of cores that you reserved. Yep, finished. So there, we could see it took us 2 minutes to run. This is an example of a fairly quick MPI job at run on node 308. Now, if you run it with 4 cores, it should finish much quicker. So this is how you would change the size of your MPI job. Back job submission failed. The scheduler is under high load, sometimes doesn't respond properly. Oh, it's done already. Okay, there was also some errors here. Potentially, when this example was written, there was different libraries here. This example was written a few months ago. Sorry about that, but what you should have seen is, you should have seen that this took somewhere around 3 times less time to run the job. Sometimes we update the libraries and other stuff on the cluster, and we have to go through and change our jobs afterwards. Are there any questions? So we could try for an MPI interactive job, question 13. We also probably want to put in, at least I do, counting group, and the fact that we're using the workshop reservation. But yeah, usually with the interactive sessions, you probably want to. It may take a few minutes. So what an interactive job here is you get immediate access. You're inside the job. And we're looking for 4 processors, and it's taking a while. So, is there any questions? Sometimes with interactive jobs, it may take a while for enough resources to become available, especially if there's a lot of other jobs running. Try it without the reservation. There we go. We're on node 552. So, with the answers to these questions, I actually have a script that shows these. And we're basically asked to look at our job IDs, number of nodes, number of processors, job node list, and so on. So, what is the job's job ID? Well, we just echo the Slurm job ID. The number of nodes, we echo Slurm num nodes. Number of processors, it's Slurm nprocs, and we can see 4. So in this NPI type job, we're using 4 processors. On which node or nodes is your job located? And it's Cedar 552. And we're using all 4 nodes. Or sorry, we're using all 4 cores of our job are on the same node. It's possible that we could have been on different nodes. You know, 1 on one and 3 on another, that sort of thing. So on how many processors per node is this job allocated? Well, we can run the command echo slurm job CPUs per node, and we'd get the answer 4. So we could do that ourselves, right? How many tasks per node is this job allocated? Once again, echo slurm tasks per node, that's 4. We could do start host name. We get 4 answers. So using srun, it runs it on every single core in our MPI job that's allocated. So that's why we got the 4 answers back. And they're the same node because all tasks of this job just happen to be on the same node for us. We could look at sq-u user, another window. And we could use user sq. Right? But in this case, user is just myself, right? But $user would be whichever user is running. And we can see that this job is running, that it has 16 minutes left, and it's using 1 node and 4 CPUs. And that it's running on node Cedar 552. Okay, you can also run an S-control command and show the job. and all kinds of information, like the fact that it's running, and it's been running for 3 minutes. Now, if you ever want to quit an interactive job, you can type in exit, or you can hit Control-D, and that terminates the job. So notice we are on the command line. It says Cedar node 5512, and then when we exit, we relinquish the allocation, and we're back onto our head node. So this is how you test jobs in interactive mode. And you can see the environment variables that are used by MPI and the scheduling system, are set by the scheduling system and used by MPI or OpenMP. Oh, okay. Question 14 is another interactive job. And we want to name it interactive, and for processes on a single node. And we're also looking for different so we want to do another salloc. But we want to put in the correct account for me, because I have multiple ones. We're back inside an interactive job. And we have a script. The script gives us actually the answers for the questions. So what are we looking at? The jobs ID. Once again, we echo Slurm job ID, num nodes for the number of nodes, num procs for the number of processors. We echo Slurm job node list. That's the list of nodes that your job's running on. We can echo how many processors per node is allocated by Slurm job CPUs per node, and we can echo the Slurm tasks per node. So here we're asking for one node with all four processors on the same node. So that's the difference between question 13 and 14. Now, it just happened in question 13 that we did end up on the same node. But it was possible that we could have had multiple ones. In this one, we always would have ended up on the same node. We'd like to do the same thing again. So for question 15, we're asked to run on one node with 12 cores. We want a new name, my interactive OpenMP job, and then we're going to look at it. So the way we do it, we ask for task equals 1, nodes equals 1, CPUs per task equals 12. We set 20 minutes, we set the correct job inside the salloc. The salloc is the same thing as the salloc is the same thing as sbatch, quite similar in the way you submit your jobs. We want to put my account there. And basically, these are the same questions that were asked before on question 13 and 14. In this case, once again, Slurm num nodes equals 1, but now num procs equals 1. Or previously, that was the number. So on which node is your job allocated? Cedar 5512. We echo how many processors per node is your job allocated on? and that's Slurm job CPUs per node, and that's 12. And how many tasks? It is 1. So in this case, we're running one task with 12 CPUs in it. And if we did the srun hostname, it's only 1, because there's only one task. But we have all 12 cores available. So right here, if we actually did go back and look at the CPU set, which we talked about yesterday, and we've got CPUs, we can actually see which CPUs were allocated. And there's 12 of them. So we have 12 CPUs where we could run it. And we could even point to which ones we're running it. So you can't step outside this sort of jail, this secret CPU set. But we can use all 12 for an OpenMP type job. Are there any questions? I'm going through this material quite quickly. So question 16 is going to be on hybrid and interactive jobs. So we're going to try to do the same thing, but with we're going to go for n task equals 3, nodes equals 3, CPUs per task equals 5. So 3 nodes with 2 tasks and 5 cores per task. This might take a little bit since we're asking for more resources. Oh no, we're in. And if we run that and look at it, we can see that we have Slurm job ID. It is right here. On how many nodes does this job run on? We just echo Slurm num nodes. It's 3. On how many processors does this job run on? We can echo Slurm num procs. That's 6. On which nodes is your job allocated? Well, we can just echo Slurm job node list, and we can see that it's Cedar 552, 556, and 692. On how many processors per node is your job allocated on? And it's echo Slurm job CPUs per node. And it's 5 times 2 and 20. And how many tasks? It's 1, 4. Yeah, 2 tasks per node. Anyway, this is a hybrid job. This is like a really it's a bigger one. I wanted to show something that would guarantee that we see different nodes here, on which nodes we're running on. It's very unlikely you're going to be, asking for 3 nodes with 2 tasks and 5 cores each. Let's here just to show that these numbers change. And how they do that. Are there any questions? Okay. We are going to go back to our presentation, and we're going to talk about Slurm jobs in memory. So it's very important that you specify memory correctly. If you don't ask for enough and your jobs use more, your job will be killed. If you ask for too much, it will take a much longer time to schedule a job, and you'll be wasting resources. So also, if you ask for more memory than is available on the cluster, your job will never run. And the scheduling system will not stop you from submitting such a job or even warn you. The scheduling system is optimistic. It thinks that somebody will come around and install a bigger node, a bigger server. Maybe then your job can run. But until somebody does that, your job will not run. So, and people are unlikely to upgrade the cluster very soon. If you don't know how much memory your job needs, your job will need to ask for, then ask for a larger amount on your first job, and then run the ssstat command here. In the max RSS, you should see how much memory your job actually used. If you don't specify any memory, then your job will get a very small default maximum memory. A few other tips about Slurm jobs in memory. Always ask for slightly less than the total memory on the node or the server, as some memory is used by the operating system, and your job will not start until there's enough memory available for your job. So if you ask for all the memory on a system, it will never be available, because some will always be used by the OS. So you may specify the maximum memory available to your job in one of 2 ways. You can ask for the total memory used by your jobs, so that's an sbatch mem equals, in this case, and the default is in megabytes. So if you do a sbatch minus mem equals 4,000, you're going to get 4,000 megabytes of total memory for your job. If you ask for sbatch minus mem per CPU equals 2,000, then you'll get 2,000 megabytes per CPU or per processor per core. Oh, what happens if you ask for minus mem equals 0? I'm not sure. I don't know if you can ask. You could try. So that's a question. I don't know if you can ask for 0 memory. That sort of doesn't make sense. But if you don't ask for memory, then you're going to get a very small amount of memory. Is there any questions? Yeah. So in our examples, we'll have a few things with memory. Slurm jobs and GPUs. So if you need to request a GPU, you could use the following syntax. Sbatch minus gress equals GPU colon 1. You could also ask for multiple GPUs. And you can also ask for large GPUs. So sbatch minus gress equals GPU colon LGPU. So Cedar has a different type of GPU that they've named large GPU, LGPU, and you can ask for those specifically. And you can ask for 4 of them. So I don't think this is actually used on Cedar, but if there are any software licenses, they could also be scheduled. So sometimes some software is limited, like MATLAB, so that people can only run a number of cores with it. In that case, you would ask for it with ---- licenses. And here we have the same things again, just in a table format. So we'll go through. For examples. Which one? Okay, question 17. Jobs in memory. So we'll take the start mem.pbs script and edit it so it asks for mem per CPU of 12,000. And here we do that. So basically, we're asking almost 12 gigabytes per core, or 48 gigabytes total. Now, the funny thing about Cedar is, if you're asking for so many cores, so much memory, you're asking for many cores worth of memory. So you're asking for a much larger fraction of the memory on the server than you're asking for in terms of cores. And the way our clusters are set up, you're going to get charged for the larger fraction, whether it's the size of the number of cores or the number of memory. So we start the job here, and we want to see what's going on. Here we're running if we run an S-control show job, what you see here is somewhere in here you should see the memory usage. Right here, we're using 48,000 megabytes. So we've asked for 12,000, but we asked for 12,000 per core. So we're actually getting 48,000 in total for the 4 cores. Okay. Question 18. we're doing the same thing, except this time we're doing a mem equals 12,000. And the mem equals 12,000 is right here. It's another job. And we do this control. And you can see here that we're using 12,000 megabytes. So this is quite a bit of a difference. You want to make sure that you ask for, when you're asking your job, that you're asking for the correct thing. If you do mem per CPU, that's per CPU. That's 4 times more than if you just do mem. Because here we're asking for total memory. And once again, mem and pmem. So memory per CPU is question 19. We're actually doing the same thing here. By the way, please ask your questions if you have any. Yeah. There's some higher level comments in the group chat about some weird use cases by some administrators or analysts in Compute Canada, but don't feel intimidated. Please definitely ask the questions. There's probably a lot more people that don't understand it. You don't understand it as well. But the idea here is we're asking for mem per CPU. And trying to figure out how much memory that job will use. Once again, just get the job ID. And here we go. So it's 12,000. So for question 20, now here's a real example of what you will often run into. And unfortunately, it's what often the basic users run into. That's one of the first things that happens. So to create a job that runs the cryptic command, so in with the tar, there was a file called cryptic. It's right here. We named it that because it just runs a program. We don't know what it is. So if you want to run a job, a simulation, you may not know what's going on. It's cryptic. How do we find out how to use the correct amount of memory? Well, we'll edit the start mem2.pbs script. So we have that here. sorry, mem2.sh script. I still have a little bit of torque in there. Should be .sh there. And if we run this, it will fail. So we have to guess how much RAM this job may need. Right here, this script only uses a single gigabyte. Sure, let's run it actually first. Dispatch. Oh yes, because I am part of multiple groups, I have to put in which group I need to use. I should probably put in the workshop as well, and I might as well put in my eval. Now we should have this start, and this is going to fail. And it's going to fail because there's not enough memory. No, and it has already failed, I think. There it is. Yeah, it's killed because we exceeded the memory limit at some point. Okay. Well, what can we do here? Well, we could do a number of things. We could give a lot more memory and see what happens, especially if we're running a large number of these jobs. We try it on one, doesn't work. We increase it quite a bit, see how much it's running. We'll look at the output, and then we'll see. Okay. Okay. So we could increase it. Headfold, for instance. Ask for 10 gigabytes. Okay. Oh, that was another job. I think we left it open. So we see that we have a running job. Okay. So as already said, it failed because we didn't have enough memory. Now, once we increase the size, we could see how much resources are being used. So we can do that a number of ways. We can run it, finish when a job runs, and look at the email that we get. That should tell us how much resources we've used, especially the memory. We can also look at SS stat and S control. So, yeah. There's the ss stat command we could get. I think that's after the job was run, though. Yeah. Oh, it finished. We can also look at the email that we get from this last job. Um, sorry. Right. I was working on this one again. Rerun this batch. And while the job's running, we'll do the stat. Again. Oh, my job isn't. These jobs may be a bit too short for us to do. There may not have been enough time for the system to actually show these jobs. But you would look at the max RSS column for this job. And you would be able to run this. In particular, the correct answer for this is 3,000, 3 gigabytes, 3,000 megabytes would run this job. You could play with this when you're doing this later. Okay, yes, as somebody said, use S account, SACCT. That's the other way, not just S stat. This shows, I guess, recently completed jobs. And you can tell SACCT to get more information. Sorry about this. I haven't run these for a while, and I usually deal with the other side of the scheduler. Start one again. And there's a column for max memory. It's quite possible that this trivial job will finish before we actually see how much it is. But for longer running jobs, it should be fairly simple. And I think we just ask for 4 gigabytes of RAM, and that will run this job. In question 21, we're asked for 1 GPU for 500 seconds. So 1 core, we basically ask for task equals 1, nodes equals 1, minus grass GPU colon 1. We also, once again, want to put the correct accounting group and the fact that we're using this special reservation so our jobs start quicker. Although I don't think we have reserved any GPUs, so I'm going to not put that in. In this one case, this isn't going to be as fast. Well, since we haven't reserved GPUs, we can't request them in the reservation. So we submit the batch. And we see that it's in state pending, so it may take a while because the GPU resources are actually pretty much all used almost all the time on the cluster. They're in high demand, so unfortunately, it may take a while for this one to start. We didn't set aside any reservations for that. Of those in the workshop. In the workshop reservation, we didn't put in any GPU nodes. So this one won't be able to be used. For question 22, well, it's not implemented on this cluster, so we don't have any software licenses on this cluster. Okay. So now we're getting into some exotic things. So what happens if you want exclusive access? Well, sometimes there's a need for exclusive access to guarantee that no other job will be running on the same nodes as your job during the debugging. Now, to guarantee that the job will run on nodes without other jobs, you own, you could use minus sbatch exclusive. Now, your research group may get charged for using the whole node and not just the resources requested. And it may take much longer time to gather the resources needed for these special jobs. So you only do this if everything else is breaking and you can't figure out what's going on, and only for the test. So if you think other jobs may be stepping on your job or something like that, only reason you would use this. This is very rare and only for debugging purposes. Now here's another one. So job submission for multiple projects. So if you're part of 2 different compute Canada projects or groups, and are running jobs for both, you may need to specify the accounting group for each project so that the correct priority of the job can be determined, and so that the usage is charged to the correct group. Because if you're charging all your usage to one group, they may not be so happy with you. If you're using the allocation that was, for one group for usage for another. And you do that with sbatch minus account equal. So as we saw with me, every time I've been running one of these things, one of these jobs, I keep putting in minus account. Now, if you are part of multiple accounting groups, or potentially if you're part of a reservation, and you just submitted a batch job, without having an account, you're going to get a big error message. And this error message is going to tell you that you're part of multiple accounting groups and that you need to actually specify which group should get charged. So in this case, as you can see, I'm part of 3 different default accounting groups, and I need to specify one of those. So I used to have that one there. If you're part of any rack accounting groups like that have any bigger allocations, well, you have to specify that as well. So there could be multiple reasons. And if you want to see all the accounting group information associated with it's as account manager show user with associations. And you could see, unfortunately, in this example here, all the accounting groups are fairly long named. You can see CC debug and so on. I think there's this very simple it's minus P. There we go. And you can see the different named accounting groups. Or you could just put in the wrong one and the system will tell you. You could also do share minus U username. And that's a much nicer output for you, actually. And you could actually see some other information. So, any questions at all? Okay. Let's go on to job dependencies. So, if you want one job to start after the another, finishes, you could use sbatch minus dependency equals after OK job ID 1. So often, it's better to break a large job into several shorter jobs because they will be often able to run faster. So you could use this technique if your job runtime is longer than the maximum wall time on the cluster or the partition. And you could submit your batch job here. And you could set the second, you could set environment variable and use that one in your second job automatically. Or you could just do it by hand. So this is the way you can make sure that your second job is available to start immediately after your first job finishes. But it won't start until after your first job finishes. Any questions? Okay. So there's also temporarily available local storage. So some software like Gaussian needs to make many small reads and writes to disk. The cluster file system cannot do this very well and becomes a performance problem with both the job and the cluster it's running on. So each node has a local disk that is shared by all the jobs running on the node. One specifies requests. Oh. No, not that way. Ah, there it is. Sorry for my notes. You do an sbatch minus temp equal and 2000 gig. That will give you the 2000 gig. Sorry, I still have some notes here from the time this was a PBS talk. Moab, not a Slurm talk. You change to the $Slurm temp directory. You can run your job, but then you want to copy your file back into your regular directory because this temporary directory will be deleted. So this is temporarily available storage while your job is running, and it disappears afterwards. But you can make use of it. And for programs like Gaussian, they have to make use of it, because if they try to read and write all those small files to the cluster file system, it would bog it down totally. Okay. Partitions. So partitions are, and by the way, please ask questions if you have any. So partitions are like queues. They're quite like queues in Moab. Your job will be automatically assigned to a partition by the scheduling system here on Cedar and Graham. There is a little bit of a difference between a partition in Slurm and a queue or class in Torque and Moab. And a job can be in multiple partitions simultaneously and can have multiple per partition priority. A node can also be in multiple partitions simultaneously. So I think most people have seen a Venn diagram. So here's a little example. Has only 2 legs. Everything in blue has 2 legs. Kangaroos, crows, sparrows, ostriches, and can fly. Everything in red can fly. Crows, butterflies, sparrows, and bees. Everything in purplish here can be both. So let's here have a partition diagram. We'll show some of the partitions here on Cedar and Graham. So let the black dots be nodes or servers. In this little example, the red partition has cores, like regular, our systems with CPUs. The blue partition has here GPUs. So all the systems have CPUs, but only some of them have GPUs. There's 5 nodes. All the 5 nodes have CPUs, but 3 of them have GPUs, and 2 nodes have CPUs but no GPUs. So a job that requires CPUs, the red partition can run on any of those nodes. a job that requires GPU is a blue part. So if it goes to the blue partition, can only run on the 3 of those. So 2 of the nodes inside the red partition may be idle, but a job that requires something in the blue partition, say GPUs, will not be able to run on those nodes even though those nodes are idle. So going through these examples, yeah. That has 3 blue nodes. Also, in the case that 2 of the nodes, so here we see these nodes in green are idle, these nodes in yellow are busy, and we can see that although there's 2 nodes that are idle, if you're in the blue partition, you can't use those. Okay. Any questions? So we'll start talking about node types in Cedar. So Cedar has 7 different types of nodes. Now the vast majority of them, 576, have 4 gigs per core, 32 cores, or 128 gigabytes of RAM. There's 182 nodes with 8 gigabytes per core, or a quarter terabyte of RAM. There's 24 nodes with 16 gigs per core, with half a terabyte of RAM. There's 24 nodes with 48 gigabytes per core, with 1.5 terabytes of RAM. And there's 4 nodes with 96 gigabytes per core, or 3 terabytes of RAM. There are also 114 nodes with 32 gigabytes of RAM, 4 GPUs. And these are called GPU base. There's 132 nodes with 64 gigabytes of memory, with 16 gigabytes of memory actually on the GPU. And they are GPU large. They're called GPU large. On Graham, thankfully, there's less nodes. There's less different types of nodes. We want lots of nodes. It's difficult to work with a large number of different types of nodes, though. So there's 800 nodes with 4 gigabytes per core, 55 with 8 gigabytes per core, 24 with 16 gigabytes per core, 3 with 96 gigabytes per core, as well as 114 GPU nodes with 4 GPUs and 32 gigabytes per core. So we have to have partitions on Cedar and Graham. Now, what do? We have some interactive partitions so that people can test their jobs. There's a few nodes there, not very many, just 3 or so. And of course, the CPUs and the GPUs are separated. So if you're asking for GPUs, you use the nodes in the GPU partition. If you ask for CPUs, you use the nodes in the CPU partition. Also, if you're asking for nodes by core, so if you're asking for whole nodes, whole sections of nodes, you could run in whole node partition. But if you're asking for nodes by core, individually by core, by pieces, you're going to be running in the by core partition. So that's one smaller. And the reason for this is because if each of those nodes have 32 cores, it would actually fragment the nodes. There would be always a core running on those nodes, and if a user required a whole node for like a Gaussian job, they would not be able to get it. As well, since we have 7 different types of nodes, we basically divided the nodes on Cedar and Graham into the nodes that use 8 gigabytes per core or less, and the nodes that use 8 gigabytes per core or more. So this is done to stop the low memory nodes from taking over those load memory jobs from taking over those nodes with lots and lots of memory, because those nodes are really expensive, and they should be preferentially running large jobs. So partitions, quite a complexity. Well, if we allowed Cedar jobs to run on all the nodes, the chances that there's a node that had all 30 cores not used or coming up to an end would be very small. So if half the cluster was empty and the jobs were distributed randomly, the chances that any particular node would be empty would be 1 over power of 2 to the 32, or about 1 in 4 billion. So as you can see, even though a half-empty cluster would not be able to easily run a whole node job, and people would have to wait a very long time for the whole node job to start. While the people that were asking for single cores, well, they would be running really quickly. That's why, what's it called, we set it up this way. And there's very little chance that a whole node job will run on the inside the bi-core area. It can, but usually there's a core being used on all the nodes there. Any questions? Another thing that we did is we based different partitions upon how long the maximum wall time is of your job. So the partitions are 28 days, 7 days, 3 days, 1 day, 12 hours, 3 hours. So if you require more than a week, you're going to be in the 28-day partition, for instance. And this reserves jobs for shorter wall time jobs. One of the reasons here is that we would like people to run shorter jobs because then people can run more jobs, there's more interaction. As we said earlier, the system is fairer, we could get better utilization, and people get their jobs back quicker. People can run a job, get the results, run another job, and if they have an iterative use case like that, they can do science faster. So that's why we have this. So we have a number of different partitions with this. And there's other advantages to running shorter jobs on how quickly your job can be started. The longer and larger the job is, the greater chances of experiencing hardware failure, and this is minimized through checkpointing. So part of the cluster is dedicated for the shorter jobs. And part of the cluster, complete Canada clusters are dedicated to whole node parallel jobs. Other jobs with shorter wall time. So even in those parts that are dedicated for whole node jobs, if you're asking for less than 12 hours, and you're asking by core, you could run in there. So if you can run shorter jobs, you'll be able to run much, much more. You'll be able to be backfilled. That means that your job will run in those areas that are dedicated for whole node jobs, because we allow shorter jobs to run there when there are no whole node jobs. Your job will fit also into the holes in the scheduling system, as we saw earlier at the very beginning, where the scheduling system naturally has holes in it. So if you can make your job take less time and get work out of it, you should actually optimize your jobs these ways. So, but why the complexity, right? Well, why do we allow long-term jobs at all? Well, we do that because some commercial codes don't checkpoint, right? And checkpoints can take a long time. So we would like to support users that run very large jobs, but we don't want them affecting all the other users on the cluster. And if we allow all the nodes to run long wall time jobs, it would take a long time for resources to become available. Researchers that needed to run short jobs and analyze the result would not be able to use the system. And people that could divide their work arbitrarily would find that running long jobs would be an advantage. And they would also start running long jobs, and that would make the situation worse. Now, Compute Canada has dealt with this situation in the past by having different clusters with different wall times and different settings. But there's not enough clusters to do this anymore. And the solution is to do these concentric partitions on larger clusters to allow us to more efficiently address diverse user needs. But then this makes the partitions, when you take in both the by node and by core, you look at the differences between GPUs and CPUs, and we look at the concentric circles. There's actually quite a few different partitions. So you get this psychedelic looking diagram. As we can see here, the really long-term running jobs are here in dark red, and they only represent a small set of the cluster. And we can actually see also that there's actually three sets: the high memory nodes, or the basic nodes that we had, right? As well as the GPUs at the bottom. So there's a lot of different partitions. So how can you see stuff on this? Well, there's a script called partition stats we wrote. This script shows you how many jobs are queued, how many jobs are running, how many idle nodes there are in each partition. So first of all, we're looking what type of jobs we have. So if you're looking for GPUs, you're just looking at the GPU line. If you're looking for regular jobs, you're looking at regular nodes, you're looking at the regular lines. And if you're looking for large men, you're looking for that. And you could look at the number of jobs that are queued, the number of jobs that are running, and so on. Also, the first number here is in the by node partition, and the second number is in the by core partition. So here we can see for the regular nodes, there is one job that is queued that requires a whole node in a queue, and there's 50 in a 3-hour partition. So first we look at the partition, 3-hour. All the jobs that use 3 hours or less, there's one job that is queued that uses a whole node, and there's 15 that use by core. However, there are 60 jobs that are running that use a whole node, and 6 that use whole core. And there are no idle nodes in this example. And the bottom section here, we have the total number of nodes in each partition. So here we can see that there's 851 nodes that a job in a 3-hour wall time can run on if it uses whole node, but only 411 if it uses a whole core, if it asks by core. However, if you're looking at the 12-hour wall time, it's 30 nodes less, right? And if you're asking for 28 days, well, there's only 90 nodes in total available. 50 of those, if you're asking for by core. So it's better off if you ask for a shorter amount of wall time. Also, these numbers are subject to change, so we tweak these numbers to make the system efficient and effective. Okay. But this could cause some issues. So in this case, there are 2 nodes with. So here we can have an example. We have partition A that has a 3-hour wall time and includes all the nodes in the cluster. Partition B is the largest partition your job can run in. And partition C is a subset of partition B. And each small green circle represents an idle node, and each small yellow circle represents a busy node. So let's assume we have 3 jobs. The highest priority job in partition C that requires 4 nodes. Now it can't run because there's only 3 empty. Second highest priority job in partition 2. Sorry, job 2 in partition A that requires 5 nodes. It can't run. And our job in partition B that it requires 2 nodes. So we could run. But what can happen is that job 1 cannot run as there are only 3 nodes, but maybe one of those nodes will be available sometime in the future. And job 2 cannot run as it needs one of those nodes reserved by job 1 start, a couple hours in the future. And our job can't run because those jobs from job A will be running, job 2 will be running after job 1. So in this system, this is a very degenerate case. This was picked exactly to be a really egregious example. We have only 30% of the nodes busy, but none of our jobs can run. And this is because we're running enormous jobs. We're running jobs that use half the nodes or more on this cluster, right? We're trying to run really big jobs. Right? So with comparison to the cluster, but this does happen in the bigger cluster as well, to a much lesser extent. So what can you do? Well, submit smaller, shorter wall time jobs. When looking at priority, why your job isn't running, look at the priority of other jobs in the partition. We haven't talked about priority yet, but we'll be able to look at that. And also that this situation in Compute Calendar will improve when Niagara is up. So Niagara is going to be a system for large jobs. So part of the reason why we have such a complicated system on Cedar and Graham is because we have to meet the needs of every single type of user that there is out there. And when we'll have more systems, we're going to be able to move the users that require to run large jobs away, and we'll be able to tune the system for the different types of users on Graham. And here are the tables. And normally I would be going through for practice. Unfortunately, I think we just run out of time. Once again, all those jobs are there for you to test, and maybe we'll go through that stuff at the beginning of tomorrow.